So we're going to wrap up our discussion of acid-base chemistry by explaining how molecular structure of acid explain the strength and the trend of the acid strength that we observe in certain types of acids. So for this, we're going to divide acids as two different types, which is binary acid, and these are acids where the acidic proton, which is the proton that it will donate, is bonded directly to an X atom. Examples of this could be Cl, HCN, HBr, HI, HF. Okay, so the anion or the conjugate base is your X atom. We're going to use the formula HX to represent a binary acid. And all the binary acids look like this. I'm showing you the Lewis structure here because this is going to be important in our discussion. And so the specific bond that we're going to focus on is the bond that connects proton and the X atom. And then we also have a second type of acids we call oxyacids. And here the acidic proton is bonded to oxygen, which is then bonded to the X atom. So any acids that have oxygens typically have this type of bonding pattern. Here I'm showing you sulfuric acid, H2SO4, and you can see that the acidic proton is bonded to oxygen. The oxygen is then bonded to sulfur. Same thing with this other hydrogen here, because that's a diprotic acid. Carbonic acid, which is shown right here in the middle, has two acidic protons, and both of them are bonded to the oxygen atom. And then this one right here is chloric acid, HClO3, and this one has one acidic proton, and that's also bonded to oxygen. The way we'll explain how acid strengths are determined will depend on two factors, and those two factors are the size of the atom that are bonded to the proton. So here on this picture, I'm highlighting the trend in ionic radii because that is the size that would determine how strong that bond is. So if you recall, the trend for ionic radii in a group as you go down a group is that it gets larger, and this is because the shell number gets larger as you come down. You might recall this discussion in Chem 11 where you have nucleus in the middle, and then each shell corresponds to each of the period that you have in the periodic table. So each of these periods right here. The other important factor that will determine strength will be electronegativity. And electronegativity pattern increases along this arrow, this red arrow that's shown right here, with fluorine, which is that element, being the most electronegative of all the elements. Now, keep in mind that the strength of the acid is going to be inversely related to the strength of that bond between the proton and either the X atom or oxygen. And the stronger the bond, the weaker the acid because it's harder to give away or donate the proton. The weaker the bond, easier to break the bond and release the proton, the stronger the acid. The length of the bond is going to be crucial because that's going to determine how strong the bond is. The longer bonds are going to be weaker and the shorter bonds are going to be stronger. That's just because the electrostatic interaction between the nucleus and the electron in shorter bonds is stronger, and then in longer bonds is weaker. This is going to be an important factor when it plays a role. So it doesn't always play a role, and it plays a role when you have these big changes in bond length. And that happens when you're going down a group like this, okay? So when you go down a group, you can see that the size changes by quite a bit. You might be able to see some of these numbers here, but for example, just look at the top number for each one of these, 136, and then 216 for iodide, ion. So you can see that going from fluoride to iodide, the size goes up by close to 70% or so. On the other hand, if you're talking about going from left to right, the changes is usually not as dramatic. That's because in a period, all the electrons are located in the same shell, so therefore the distance difference is not that major. So size is going to be an important factor when you go up and down a group in terms of the strength of the bond, whereas electronegativity is going to be more important when you go left and right, because at that point the size is about the same, so the electronegativity becomes the critical factor. And that's exactly what I mentioned here. When the length of the bonds are similar, then electronegativity is more important. The ion size increases dramatically when you go down. This is a picture of the size of the fluoride ion versus the iodide ion. You can see that the size is a lot larger for iodide, and as a result, the bond between the proton and the ion, which is to the center of each of these spheres right here, you can see that that bond would be a lot longer for iodide, which is for hydroiodic acid, versus hydrofluoric acid, and thereby making this acid the stronger acid. Electronegativity will play an important role in other contexts when the sizes is about the same, but not in this case because the size is just so much different that it becomes the only factor that matters. We can see that that is the case for binary acids because when we look at these trend going down this group, this is the halogen acid FCl, Br, and I, you can see that despite the fact that the electronegativity increases the other way, so when the electronegativity increases, the bond gets more polar between the H and the X, and that should make the acid stronger. But despite the fact that the electronegativity increases this way, the acid strength goes the opposite way. It goes this way. So the stronger acid is HI, and then the weakest acid in this particular group is HF. You can see it in the bond strength. So the bond strength itself, the weakest bond is HI, so 295 kilojoules per mole. HF has the strongest bond. So in fact, that size just overpowers electronegativity. We see it in the Ka, of course, which in this case is expressed as pKa. So remember that pKa is just negative log of Ka. So if you get a positive number, that means your Ka is less than 1. If you get a negative number, that means the Ka is actually bigger than 1. So these are really strong acid when their pKa is negative, and then it's weaker acid when the pKa is positive. Now, when you're talking about going across period in the periodic table, this is where electronegativity becomes the dominant factor. And the reason is because the valence shell remains the same for all the elements when you go across a period. For example, in this period right here where we have carbon, nitrogen, oxygen, and fluorine, they're all second period, right? So therefore, the sizes of these ions are not going to change by a whole lot. They're going to be different, but it's just not going to be a whole lot. You can actually see it. So this here is the actual bond distance between H and each one of those X atoms. And there's a difference, but it's not a huge difference, okay? It's probably about 10 to 20% difference. Whereas when we go down that group, we go from 92 to 160, which is almost a doubling, right? So like I said, about 70% difference earlier. So much less difference when you go across a period. Now you have to look at electronegativity to explain acid strength and its trend. And again, the idea here is that the larger the difference in electronegativity, which we give the symbol delta En, you might recall this from Chem 11, between the H and the X atom, the more polar the bond, and the more polar the bond, the easier it is to break, and so the acid is going to get stronger. So when we go left to right, electronegativity increases, so we would expect HF to be the strongest acid in this group as you go from left to right. And of course, that is indeed the case because NH3 is actually not even an acid, it's a base. H2O, which is when H is bonded to O, it's not an acid or a base, it's just a neutral compound, and then HF is the only acid in that whole group. Okay, so in fact, when we go left to right, we see acid strength increases. And then when we go top to bottom, we also see acid strength increases. But then the explanation for this increase in acid strength is different depending on whether we're explaining it for the period or whether we're explaining it for the group. We see it, of course, expressed in the pKa values again. So again, as a reminder, the pKa value represents acid strength, but then the more positive the pKa value is, the bigger the value is, the weaker the acid, right? Because again, pKa is negative log of Ka. So just keep that in mind that the smaller the Ka is, the more positive the pKa is. So therefore, this is the weakest acid. This is the strongest acid. Now let's take a look at oxyacid. Oxyacids is different from binary acids because the hydrogen or the proton is bonded to oxygen, and then the oxygen is bonded to the X atom. So in other words, the hydrogen is not directly bonded to X, so X can change. It could be Cl, could be Br, could be I, but that's not going to affect the bond between H and O, right? Because H is always bonded to O. So the size of the atom that's bonded to the proton doesn't change. So therefore, size is no longer a factor here. So the only factor is electronegativity and the polarity of that HO bond. That's what matters. Again, the more polar the bond, the weaker it is, the easier it is to let go of the H, the stronger the acid. There are two factors that affect the polarity of the HO bond. One is just the number of oxygen atoms. So oxygen itself is a highly electronegative element. So the more oxygen you have, the more it pulls on the electron. So if we go back up to that structure of, say, sulfuric acid, if I have more oxygen, each of these oxygens is going to pull electron to itself because it's electronegative, and it then causes all the other electrons to get pulled in, including the electrons that between the O and the H here. This is something we refer to as inductive effect. It's just a pull of electrons or attraction for electrons through a bunch of bonds, and that occurs in these acids. And so if you're comparing something like H2SO3 versus H2SO4, you would say that H2SO4 is a stronger acid because it has more oxygen. Another example would be HNO2 versus HNO3. In this case, HNO3 is a stronger acid. The other factor that matters is the electronegativity of the X atom. So if you have more electronegative atom bonded to the oxygen, then that's going to also exert an inductive effect. It's going to pull the electron, and it's going to result in a stronger acid. So here we're talking about things like if you have HClO3 versus HBrO3, for example. So the trend of electronegativity is, again, this one right here, right? So if you look at Cl, it's going to be more electronegative compared to Br, so that the HClO3 acid is going to be a stronger acid than HBrO. Okay, I'm going to show you this table right here, which shows several of these oxyacids, and I want to point out some of the ones that we can compare to show the effects of both the number of oxygen atoms as well as the electronegativity of the X atom. So let's take a look at, here's HClO2 chlorous acid, and here's hypochlorous acid, HClO, right? So one has more oxygen, the other one has fewer oxygen. You can see that this one has a Ka of 1 times 10 to the minus 2, whereas this one has a Ka of about 10 to the minus 8. So clearly having that one extra oxygen actually makes it quite a bit stronger, quite a bit of stronger acid. They're both weak acids, but the chlorous acid is much stronger. If you look at, as I said earlier, HNO2. HNO2 is not even listed here because it's a strong acid, right? It has a Ka that's bigger than 1. But HNO2 has a Ka that's 10 to the minus 4. HNO3, on the other hand, is like up here. That's where the Ka of HNO3 lies. Okay, so those are a couple of examples for number of oxygen. What about the electronegativity of the X atom? Well, you can compare, for example, HBrO with HClO. As I said earlier, Cl is more electronegative than Br, so this is a stronger acid compared to HBrO. HIO is even less electronegative, right? I is less electronegative, so here's actually the part of the periodic table that shows the halogen and the electronegativity values of all of these halogens. You can see that Cl has electronegativity of 3.16, Br 2.96, and I 2.86, and so HIO, which has the least electronegative X atom compared to the other one, has also the weakest acid here, so has a Ka of about 10 to minus 11. So hopefully that explains and allows you to predict, if somebody gives you a comparison of 2 or 3 acids, they all have same X atoms but different numbers of oxygen, for example, you can predict who's going to have a stronger acid, who's going to have weaker acid, and so on. Okay.